Tonight, we're going to explore something quiet. Not an explosion. Not a flash of light in the sky. Not a comet, or a black hole, or a rogue planet drifting through the dark. Nothing dramatic enough to make the evening news. Just a number, sitting slightly out of place, inside a mountain of data so large that no human being will ever look at all of it directly. Somewhere beneath the border of France and Switzerland, 100 meters under vineyards and farmland and quiet alpine villages where people are, right now, going to sleep in their beds without knowing anything unusual is happening beneath their floors, there is a ring of magnets 27 kilometers around, cooled colder than deep space, built to smash protons into each other at nearly the speed of light, over and over, 1 billion times a second, in the hope that somewhere in that violence, nature will let something slip. For 50 years, nature has not let much slip. For 50 years, a set of equations known as the Standard Model of Particle Physics has predicted, with almost unreasonable precision, the outcome of nearly every experiment ever run. Every particle it said should exist. Existed. Every force it described behaved exactly as described. Generation after generation of physicists have tried to catch this theory making a mistake, and for 50 years, it hasn't. Not once. Not really. Until, perhaps, now. In December of 2025, a team of physicists working with a detector called LHCb quietly finished counting something almost unimaginable. Roughly 650 billion decays of a short-lived, unstable particle called a B-meson. Somewhere inside that mountain of decay events, in a corner of the data most people will never hear about, they found a pattern. A small, persistent, stubborn wobble. A place where nature was not behaving quite the way the 50-year-old rulebook said it should. It is not a new planet. It is not a new particle you can point to. It is something stranger, and in some ways more unsettling. A whisper, buried in 500 billion events, that the most successful scientific theory in human history might, for the very first time in decades, be showing a genuine crack. For decades, scientists believed the rulebook was complete enough to explain almost everything they could reach with their instruments. Then they found something the rulebook did not predict. The first surprise was how far the deviation drifted from what the equations demanded. The second was that an entirely separate detector, built by an entirely separate team, using entirely different technology, found the same drift independently. And the third, the quietest, and in some ways the most human part of this story, is that physicists have stood in this exact spot before, excited, cautious, hopeful, and been wrong. By the end of tonight, you're going to understand exactly what was measured at CERN, what a penguin decay is, and why it has that name, why physicists measure their confidence in units called sigma, why the number 4 is thrilling and the number 5 is sacred, and why this single small tremor in the data might be either the beginning of the next revolution in physics or the latest in a long, humbling list of ghosts. Settle in. Let your shoulders drop. There is no need to follow every number closely. The shape of the story will carry you. We have several hours together tonight and nowhere else to be. Here is where we are going. We will begin at the very foundation. The rulebook itself, the standard model, and the strange, quiet, 50-year winning streak that makes tonight's story worth telling at all. We will walk, slowly, through the machine built to break that rulebook. A detector the size of a cathedral, purpose-built to watch a single, almost absurdly rare event, one in every million decays of a particle that no longer exists a trillionth of a second after it forms. We will look closely at what was actually seen. Not headlines, not exaggeration, but the real measurement, the real number, and the real uncertainty that comes with it. We will sit with the sobering history of science's false alarms, the moments physicists were sure, and the universe quietly proved them wrong. We will follow the thread outward, from a single decaying particle to one of the deepest unsolved mysteries in all of physics, why anything exists at all rather than nothing. And we will end, as we always do, by turning that question back toward ourselves, toward what it means to be a conscious, thinking form of matter, built from the same particles under investigation, alive at the one particular moment in cosmic history when a species finally has the tools to ask these questions. Before we dive in, if the mysteries of the universe are the kind of thing that helps quiet your mind at the end of a long day, consider liking this video or subscribing to the channel. It's a small thing. It costs you nothing. But it helps this kind of slow, patient science storytelling reach the people who need exactly this tonight. Now, let's begin. To understand why a single wobble in a mountain of data could matter so much, we first need to understand what exactly is being challenged. So let's go back. Not to December 2025. Further than that. Let's go back to the middle of the 20th century, to a period when physics was, frankly, a mess. Particle accelerators were starting to come online around the world, and every time physicists turned one on and looked closely at the debris of a collision, they found more particles. New ones. Particles nobody had predicted, with strange properties appearing and vanishing in fractions of a second. For a while, it seemed as though nature simply had an endless drawer of particles, and every time physicists opened it, there was another one inside, with no obvious reason for why it existed or how it related to anything else. It was chaotic. It was, by most accounts, a little embarrassing. There were so many particles by the 1960s that one physicist reportedly joked that if he could remember the names of them all, he would have become a botanist instead. Physicists at the time sometimes called it, only half-jokingly, the particle zoo. Every new accelerator, every new experiment seemed to open a new cage. Pions, kaons, lambda particles, sigma particles, Xi particles. Each one with its own mass, its own charge, its own lifetime, its own peculiar way of decaying, and no obvious family tree connecting any of them to any of the others. It felt, to many of the physicists living through it, less like uncovering the fundamental architecture of nature and more like being handed an ever-expanding, poorly organized stamp collection. The first real crack of order came from a physicist named Murray Gell-Mann, who noticed, in the early 1960s, that if you arranged these particles according to certain shared properties, charge, a quantum property called strangeness, and a few others, they fell into surprisingly tidy geometric patterns. Groups of 8. Groups of 10. He called the scheme, with a touch of poetry, the Eightfold Way, borrowing the phrase from Buddhist philosophy. And the patterns worked so well that they made a prediction. A particle with a specific, previously unseen combination of properties should exist, sitting in an empty slot in one of these geometric arrangements. Physicists went looking for it. In 1964, they found it exactly where the pattern said it should be. It was called the omega- particle, and its discovery was one of the first real hints that the particle zoo wasn't chaos at all. It was a code waiting to be cracked. Gell-Mann, along with a physicist named George Zweig working independently, pushed the idea further, proposing that all of these seemingly separate particles were not, in fact, fundamental at all. They were combinations of smaller, more basic building blocks. 3 of them, at the time, which Gell-Mann named quarks, borrowing the word, almost at random, from a line in James Joyce's novel Finnegan's Wake. For a few years, quarks remained a purely mathematical convenience, an elegant piece of bookkeeping that made the patterns work, without clear proof that quarks were physically real objects rather than a useful accounting trick. That changed in 1968 at the Stanford Linear Accelerator Center in California, where physicists fired high-energy electrons directly at protons and watched how the electrons scattered. If a proton were a smooth, uniform ball of matter, the electrons should have scattered gently, in predictable, smooth patterns. Instead, some electrons bounced back sharply, violently, at wide angles. the unmistakable signature of striking something small, hard, and concentrated inside the proton, rather than something soft and uniform. It was, physicists realized, direct experimental proof that protons were not fundamental particles at all. They were made of something smaller. Quarks were real. And then, slowly, across roughly a decade and a half, from about 1961 to 1974, a small group of theoretical physicists did something remarkable. They found the pattern underneath the chaos. 3 of them: Sheldon Glashow, Steven Weinberg, and Abdus Salam, showed that 2 of the 4 fundamental forces of nature, electromagnetism and something called the weak nuclear force, were not actually separate forces at all. At extremely high energies, they were the same force, wearing 2 different masks. This was the electroweak unification, and it was one of the most elegant achievements in the history of physics. Around the same time, physicists were also cracking open the particles themselves, discovering that the protons and neutrons inside every atomic nucleus in your body were not fundamental at all. They were made of smaller particles called quarks, bound together by a separate force called the strong nuclear force, described by a theory called quantum chromodynamics. Piece by piece, discovery by discovery, these ideas fused together into a single framework. Physicists gave it a name that, honestly, undersells what it actually is. They called it the Standard Model. It is, without much exaggeration, the most successful scientific theory ever constructed by human beings. Here is what it says exists in its entirety. 6 types of particles called quarks: up, down, charm, strange, top, and a particularly important one for tonight's story called beauty, or sometimes bottom. 6 particles called leptons: the electron, the muon, the tau, and 3 ghostly, almost massless particles called neutrinos that pass through you, through the Earth, through entire planets, by the trillions, every single second, almost never interacting with anything at all. 4 force-carrying particles called gauge bosons: the photon, which carries electromagnetism, the W and Z bosons, which carry the weak force, and the gluon, which carries the strong force, gluing quarks together inside every proton and neutron in existence. And finally, one more particle, discovered only within living memory: the Higgs boson, the particle responsible for giving many of the others their mass in the first place. 17 particles. That's the entire inventory. Everything you have ever touched, tasted, seen, or been, all the way down, is built from combinations of those 17 entries. And the truly remarkable part is not the list itself. It's what the list has done, decade after decade, when physicists have tried to catch it out. In 1974, the theory predicted the existence of a particle called the charm quark before anyone had directly observed it, and shortly afterward, it was found exactly where the mathematics said it would be. In 1983, physicists at CERN discovered the W and Z bosons, the very particles that carry the weak force, with masses matching the theoretical prediction closely enough to win a Nobel Prize the following year. In 1995, the top quark, the heaviest of all 6 quarks, was discovered at Fermilab in the United States, again exactly where predicted. In 2000, the tau neutrino, the last of the 6 leptons still unseen directly, was finally observed. And then, on the 4th of July, 2012, in an auditorium at CERN packed with physicists who had waited their entire careers for this moment, 2 independent detectors, ATLAS and CMS, jointly announced that they had found a new particle with a mass of about 125 times the mass of a proton. It was the Higgs boson, predicted on a chalkboard in 1964 by Peter Higgs and, working independently, Francois Inglet and Robert Brout, confirmed in a tunnel under the Swiss-French border 48 years later. 48 years between a piece of mathematics and its physical confirmation. Think about that for a moment. Somewhere in 1964, a physicist wrote down an idea about why particles have mass, an idea so abstract it would take nearly half a century, and a machine larger than most cities' downtown districts to actually verify it was true. And it was true, exactly as predicted. With the Higgs discovery, the Standard Model was, in a very real sense, complete. Every particle it predicted had been found. Every force it described had been measured, tested, and confirmed to extraordinary precision again and again in thousands of separate experiments in laboratories all over the world for over half a century. It has never lost a head-to-head contest with reality. Not once. And physicists have been actively, deliberately, enthusiastically trying to break it for 50 years. Because a broken piece of the Standard Model is exactly what a career-making discovery looks like. And yet, here is the strange, quiet tension sitting underneath all of this success. Physicists will tell you, almost apologetically, that despite this unbroken winning streak, the Standard Model is known, with total certainty, to be incomplete. It cannot explain gravity. General relativity, Einstein's theory of gravity, sits completely outside the Standard Model's mathematics, unreconciled, a separate rulebook for a force the Standard Model has no way of describing at the quantum level. It cannot explain dark matter, the invisible substance that appears from its gravitational effects on galaxies to make up roughly a quarter of everything in the universe, and for which the Standard Model offers not a single candidate particle. It cannot explain dark energy, the mysterious force driving the accelerating expansion of the universe, which makes up roughly 2/3 of all the mass and energy that exists, and again, the Standard Model has nothing to say about it. It cannot explain why the universe is made of matter at all, rather than being empty. A puzzle we will return to later tonight, because it turns out to sit closer to this story than you might expect. And it cannot explain why neutrinos have mass. A very small mass, but a real one, confirmed by experiment. When the original Standard Model equations predicted, cleanly and unambiguously, that they should have none at all. So here is the shape of the puzzle physicists have been sitting inside for 50 years, a theory that describes, with staggering precision, everything we can currently measure, while openly, admittedly, describing only about 5% of everything that actually exists in the universe. 95% of reality sits outside its pages entirely. It is, in other words, a book that has never once been caught making an error, while everyone who has read it agrees it is clearly missing chapters. And for 50 years, physicists have been hunting for the seam, the place where the missing chapters connect to the ones we already have, the place where, if you looked closely enough, you might catch the rulebook admitting it doesn't know everything. That is the hunt this story is about. Before we move on to the machine at the heart of tonight's story, it's worth spending a little more time with the Standard Model's 50-year winning streak, because the weight of tonight's anomaly only really makes sense once you understand exactly how rarely and how narrowly this theory has ever been caught off guard. Let's walk through a few of these victories slowly, because each one, on its own, was once a moment of genuine, nail-biting uncertainty for the physicists living through it. In 1983, at CERN's older accelerator, a machine called the Super-Proton Synchrotron, two teams led by physicists Carlo Rubbia and Simon van der Meer went looking for two particles the electroweak theory demanded must exist: the W and Z bosons, the carriers of the weak nuclear force. The theory predicted not just that these particles existed, but roughly how massive they should be. A very specific, falsifiable number published years earlier that the experiment would either confirm or destroy. There was no ambiguity in what would count as success or failure. Either the particles would show up at close to the predicted mass, or the electroweak theory itself would be in serious trouble. They showed up. First, the W boson in January of 1983, then the Z boson a few months later in June. Both arriving at masses matching the theoretical prediction closely enough that Rubbia and van der Meer were awarded the Nobel Prize in Physics the very next year. An unusually fast turnaround for a Nobel, reflecting just how cleanly and decisively the prediction had been confirmed. 12 years later, in 1995, physicists working at Fermilab's Tevatron Collider outside Chicago finally cornered the heaviest of all 6 quarks, the top quark. It had been theoretically required since the 1970s. The missing partner needed to complete the pattern of 3 quark generations, but it took 2 decades of ever more powerful accelerators to actually produce one, because the top quark turned out to be extraordinarily massive, roughly as heavy as an entire atom of gold, packed into a single fundamental particle, far heavier than physicists had originally guessed. When it was finally found, its mass, once again, matched what indirect measurements, subtle quantum effects the top quark's mere existence should have on other, already measured particles, had predicted years in advance. The theory hadn't just said the particle existed, it had correctly guessed its weight before anyone had ever seen it directly. And in the year 2000, the very last piece of the leptons, the tau neutrino, the ghostly, nearly massless partner of the heaviest lepton, was finally observed directly at an experiment called Donut, also at Fermilab, closing out the full roster of fundamental particles required by the electroweak portion of the theory, 12 years before the Higgs boson would complete the picture entirely. Every one of these discoveries carried real risk. Real careers were staked on outcomes that were not guaranteed. Real experiments were designed, funded, and built specifically with the possibility in mind that they might fail to find anything at all, that the theory, elegant as it was on paper, might simply be wrong. And every single time, across 5 decades, in 5 separate, high-stakes tests, the theory won. This is the opponent tonight's 4 sigma anomaly is up against. Not a fragile, untested idea. A theory that has already survived exactly this kind of scrutiny, under exactly this kind of pressure, 5 times over, and come out the other side unbroken every time. That is what makes this story worth telling carefully, rather than sensationally. To hunt for a seam in a rulebook this successful, you cannot simply look harder at the things the rulebook already explains well. You have to find the place where it is weakest. The place where, if something new and invisible exists, it would leave the faintest possible fingerprint. That place, it turns out, is not a big, violent collision. It's the opposite. It's something almost absurdly small and quiet. The way a particular, unstable particle chooses to fall apart. Let's talk about the machine first, because the machine itself is worth sitting with for a moment. Let it unfold slowly. The Large Hadron Collider is a ring 27 kilometers in circumference, buried about 100 meters beneath the countryside outside Geneva, straddling the border between Switzerland and France. If you walked its full loop at an ordinary walking pace, without stopping, it would take you the better part of 6 hours, and you would spend that entire walk underground, beneath vineyards, farmhouses, quiet roads, and small villages where residents go about entirely ordinary lives, almost never thinking about the machine running silently beneath their feet. Inside that tunnel, twin beams of protons travel in opposite directions, guided around the ring by more than 9,000 superconducting magnets. For these magnets to become superconducting, to carry enormous electrical currents with zero resistance, they must be cooled to just under 2 degrees above absolute zero, using more than 100 tons of liquid helium circulating continuously through the tunnel. That temperature, a hair's breadth above absolute zero, is colder than the average temperature of empty interstellar space itself, which sits at around negative 270 degrees Celsius. The tunnel beneath the French-Swiss border is, in a very real sense, one of the coldest sustained places anywhere in the known universe, colder than most of the universe around it. At full power, these magnets generate magnetic fields roughly 100,000 times stronger than the Earth's own natural magnetic field, strong enough to bend 2 beams of protons, each carrying the energy of a moving freight train compressed into a beam narrower than a human hair, around a 27-kilometer circle without ever letting them drift off course. The protons circulating in each beam are accelerated until they are moving at 99.9999991% of the speed of light, close enough to light speed that each proton completes over 11,000 full laps of the 27-kilometer ring every single second. At 4 points around this ring, the two beams are steered directly into each other and allowed to collide. Around each collision point sits a detector, a machine, essentially, built to watch an explosion of subatomic debris and reconstruct, particle by particle, exactly what happened in the collision that produced it. When the LHC is running at full intensity, roughly 1 billion of these proton-proton collisions happen every single second at each collision point, far too many for any detector to record in full. Sophisticated, near-instantaneous filtering systems, called triggers, make split-second decisions many times per second about which handful of collisions out of that billion are worth keeping and which should be discarded forever, unrecorded, the instant they happen. It is, by any reasonable measure, one of the most complex machines human beings have ever built. A joint undertaking of thousands of scientists and engineers from over 100 countries, operating continuously around the clock for the sole purpose of watching, closely, what happens when matter is pushed to the most extreme conditions currently achievable anywhere on Earth. Most people who have heard of the Large Hadron Collider have heard of two of these detectors, ATLAS and CMS, the two general-purpose giants that jointly discovered the Higgs boson in 2012. But tonight's story centers on a smaller, more specialized detector tucked into the ring since 1994 called LHCb. LHCb is not built like the other detectors. Where ATLAS and CMS are built like barrels, wrapped symmetrically all the way around the collision point to catch debris flying in every direction, LHCb is shaped more like a cone, or a spectrometer pointed in a single forward direction. This unusual shape exists for a specific reason. The particles LHCb is built to study. Heavy particles containing a type of quark called the beauty or bottom quark tend to be produced flying predominantly forward in the same general direction as the original proton beam. LHCb was purpose-built geometrically to catch exactly those particles in exactly the direction they tend to go. And what LHCb watches for, specifically, is a very particular kind of decay. Here's what you need to picture. When two protons collide at nearly the speed of light, the energy of that collision can, briefly, conjure new particles into existence. Among them, particles called B mesons. A B meson is a short-lived, unstable pairing of a beauty quark and a lighter quark, bound together for an almost inconceivably brief moment before falling apart. On average, a B meson survives for about 1.5 picoseconds, 1.5 trillionths of a second, before it decays into other, lighter particles. Most of the time, when a B meson decays, it does so in ways the standard model predicts perfectly, down to the tiniest detail, with no surprises whatsoever. But every so often, roughly once in every million decays, a B meson decays in a specific, rare way. It transforms into a particle called a K-star meson, along with a pair of muons, a heavier cousin of the electron. This particular decay, written as B0 to K-star mu plus mu minus, is the decay at the center of tonight's story. And here is why physicists care so much about something that happens only once in every million events. It's not because the decay itself is exotic. It's because of what has to happen, quantum mechanically, for that decay to occur at all. We'll walk through exactly what that means next. But first, here's what scientists expected to find, going into this measurement, based on 50 years of an unbroken winning streak. They expected the rulebook to hold. Before we get to what was actually found, we need to sit with a strange little piece of physics history, because the decay at the heart of tonight's story is known officially in published scientific papers, in peer-reviewed journals, by physicists with doctorates from the world's most prestigious universities as a penguin decay. It is genuinely one of the odder names in all of science. And the story behind it is worth telling slowly, because it tells you something true about the people doing this work. That behind the equations and the sigma values, this is still a human enterprise, done by human beings, with human senses of humour. In 1977, a CERN theoretical physicist named John Ellis lost a bet over a game of darts in a pub near the laboratory to a physicist named Melissa Franklin. The terms of the bet required him to work the word penguin into the text of his next published physics paper. Being a physicist of some integrity, he honoured the bet. But the word needed a home, some genuine reason to appear in a serious paper about quark decays. And so, looking at a particular class of Feynman diagrams, the little sketches physicists use to represent particle interactions, where a quark loops briefly through a virtual particle before emitting something else. Ellis reportedly had what he later described as a sudden flash of recognition. The diagrams, with their looping lines curling back on themselves before a small emission at the top, looked, to him, unmistakably like penguins. The name stuck. Permanently. It is not a nickname used casually among physicists over coffee. It is the formal, published, peer-reviewed term. There are papers with titles like Electroweak Penguins, sitting in respected physics journals to this day, all tracing back to a lost darts bet at a pub outside Geneva in 1977. So, with the name explained, what is a penguin decay, physically? Here is the quantum mechanical shortcut version, and I want you to picture it slowly, because the picture matters. In our B meson decay, a beauty quark needs to transform into a strange quark. But here's the problem. In the standard model, a direct transformation from a beauty quark straight into a strange quark is forbidden. It simply cannot happen in a single direct step, what physicists call at tree level. So instead, nature takes a detour. The beauty quark briefly, fleetingly, transforms into a virtual W boson and a virtual top quark. Particles that exist for a duration so short they are almost a bookkeeping fiction, a mathematical loop rather than a physical journey. Before the loop closes and a strange quark, along with a pair of muons, emerges on the other side. It is, in effect, a hidden quantum backdoor. The beauty quark cannot walk straight through the front door into being a strange quark. So it slips out through this brief, looping side passage instead. And this is precisely why physicists care about penguin decays so much. Because that brief quantum loop, that side passage, is a place where anything could be hiding. Any undiscovered particle, any unknown force, anything beyond the 17 entries in the standard model's inventory could, in principle, insert itself into that loop for its own fleeting moment and leave behind a measurable fingerprint in how often the decay happens, and in exactly what angles the resulting particles fly apart from each other. AB meson, in other words, is a messenger, a tiny, unstable envelope carrying, encoded in the statistics of how it falls apart. Information about physics we cannot reach directly with any collider currently on Earth. Which brings us to what LHCb actually measured. Physicists don't just count how often this decay happens. They measure something more subtle. The precise angles at which the 4 resulting particles fly apart from the collision point across many thousands of individual decay events. From these angles, using a carefully constructed piece of mathematics, they build a quantity called P5', a specific combination of angular measurements engineered by theorists over many years to be as insensitive as possible to certain messy, hard-to-calculate effects, so that if new physics is hiding in that quantum loop, its fingerprint would show up clearly in this one number, and in a specific range, where the invisible energy carried away in the collision falls between roughly 2 and 8.5 units on the scale physicists use. The measured value of P5' has, for over a decade now, been landing in a place the standard model does not predict. Not randomly scattered around the prediction, the way statistical noise would look. Consistently, persistently, below it. A systematic misalignment. Not a jitter. A wobble with a direction. Physicists first noticed this wobble in 2013 using an early batch of data. They confirmed it again in 2015 with a fuller analysis. They confirmed it again in 2020 with even more data added, each time using more B mesons, more decay events, more statistical power. The wobble did not go away. And then, in December of 2025, came the measurement this entire story is built around. Let's slow all the way down here, because this is the number the entire story hinges on, and it deserves to be understood properly, rather than simply repeated. In December 2025, the LHCb collaboration submitted the most complete analysis of this decay ever assembled, combining 11 years of data collected between 2011 and 2018 across two separate operational periods of the collider known as Run 1 and Run 2. In total, the analysis rested on approximately 650 billion B meson decays. Say that number slowly. 650 billion. If you tried to count that number of decays, one per second, without stopping to sleep or eat, it would take you over 20,000 years. Physicists did not count them one at a time, of course. The detector and its software did the counting, but the scale of the dataset is worth sitting with because it's the foundation for everything that follows. Out of those 650 billion decays, only a tiny sliver, roughly 1 in every million, decayed in the specific penguin pathway this story is about. And it's worth pausing here on a small but important correction, because a widely repeated version of this fact gets it wrong. Some early popular reporting claimed this decay happens only once in a billion. It doesn't. The actual figure, confirmed by the physicists who ran the analysis, is closer to 1 in a million. The 1 in a billion figure belongs to a completely different part of tonight's story. One we'll return to later when we talk about why matter exists in the universe at all. Keep that number in your back pocket. We'll need it again. From that sliver of rare decays, physicists extracted their angular measurements, calculated P5' across the relevant range, and compared it, finally, against what the standard model predicts. And the two did not match. The tension between the measurement and the prediction, once every source of experimental and theoretical uncertainty was accounted for, came out to approximately 4 standard deviations. In the language physicists use, 4 sigma. Now, what does 4 sigma actually mean? Let's walk through it carefully, because this single unit of measurement is going to matter enormously for the rest of tonight's story. In particle physics, sigma is a way of expressing how surprising a result is, assuming the boring explanation is true, assuming there is no new physics at all, and what you're looking at is simply the ordinary, expected statistical noise that shows up any time you run an experiment. 1 sigma is unremarkable. It's the kind of small deviation you'd expect to see roughly 1 time in 6, just from chance alone. Background noise, nothing more. 2 sigma starts to catch a physicist's eye. Interesting, perhaps, but still well within the range chance alone would regularly produce, about 1 in 44. 3 sigma is what physicists formally call evidence. It's a real signal worth taking seriously and continuing to investigate, corresponding to roughly a 1 in 740 chance of being a random fluctuation. 4 sigma, where our story sits tonight, is stronger still. It corresponds to roughly a 1 in 15,700 chance that what's being seen is pure statistical noise, with no real cause behind it at all. Strong enough that most physicists in the room start paying very close attention. Strong enough to justify pouring years of additional effort into collecting more data. But, and this is the crucial word tonight, not yet strong enough to declare victory, because there is one more threshold above it. And in particle physics, that threshold is treated with something close to reverence. 5 sigma. The formal, internationally recognized bar for declaring a discovery, a threshold corresponding to roughly a 1 in 3.5 million chance that the effect being measured is nothing more than an unlucky roll of the statistical dice. To help this land, here's an analogy some physicists use. 5 sigma is a coincidence so extraordinarily rare that even after you account for every conceivable way scientists could be fooling themselves, bad statistics, an unnoticed detector flaw, an unlucky choice of which piece of data to look at most closely, the result still looks real. It is not just unlikely, it is the kind of unlikely that survives skepticism. 4 sigma is not that. 4 sigma is compelling. 4 sigma is exciting. 4 sigma is the kind of number that makes physicists reorganize their research priorities and apply for more beam time. But 4 sigma has, historically, also been the exact number at which some of the most talked about discoveries in the history of particle physics have quietly evaporated. We are going to spend real time with that history tonight, because it is the emotional and intellectual center of this entire story. Not the number itself, but the discipline of not believing the number too quickly. But before we go there, we need to understand one more piece of the puzzle, because 4 sigma, measured by one experiment, is a strong signal. 4 sigma, measured independently by 2 separate experiments using 2 entirely different machines, is something else altogether. And that, as it happens, is exactly what happened next. Here is something important to understand about how modern particle physics actually works, day to day, behind the scenes. LHCb is not the only detector on the Large Hadron Collider capable of studying B meson decays. CMS, one of the 2 giant general-purpose detectors that co-discovered the Higgs boson back in 2012, can also, when it points its enormous barrel-shaped apparatus at the right kind of collision, reconstruct this exact same rare decay and measure this exact same angular observable. And CMS did. Using an entirely separate data set, 140 inverse femtobarns of collisions, a unit physicists use to describe the total amount of collision data gathered, collected during what's called Run 2 of the collider. The CMS collaboration ran its own, fully independent version of this measurement. Different detector, different hardware, different trigger systems, which decide, in real time, which collisions are interesting enough to record out of the billions happening every second. Different reconstruction software, written by different teams of physicists, most of whom had never worked directly with their counterparts on the LHCb side. Different collaborations of scientists entirely, publishing under a different collaboration name, answering to different internal review processes. And when they finished their analysis and compared it to the standard model, they found the exact same thing, in the exact same range. A p5 prime value sitting below prediction. The same wobble, the same direction, the same general location in the data. CMS's version of the measurement carried larger uncertainties than LHCb's. Their dataset, while enormous, wasn't purpose-built the way LHCb's forward geometry is, so on its own, CMS's result doesn't reach 4 sigma. But it didn't need to stand alone. It needed to agree. And it did. Here's why that agreement matters so much more than it might first appear to. Imagine 2 completely separate weather stations in 2 completely separate towns, built by 2 completely different companies, using 2 completely different sets of instruments, staffed by 2 completely different teams who have never spoken to each other. Now imagine both stations, independently, on the same afternoon, report an unexplained temperature spike in a specific patch of forest between them. One station reporting something strange might mean a faulty thermometer. 2 independent stations, with different equipment and different teams, reporting the same anomaly in the same place. That's a different kind of evidence entirely. It doesn't prove the anomaly is real, but it makes the faulty equipment explanation dramatically less likely, because it would require both separate, independently built systems to happen to fail in exactly the same way, in exactly the same place, at exactly the same time. That is what happened here. CERN's own official summary of the analysis, released in September 2025, stated plainly that the LHCb results were in good agreement with this recent independent CMS measurement. 2 witnesses, different instruments, different teams. The same story. It would be very tempting, at this point in tonight's journey, to declare the mystery solved, to say that the standard model has finally been caught. 2 independent detectors have agreed. The number is 4 sigma. Surely, this is the moment physicists have been waiting 50 years for. But it isn't. Not yet. And the reason it isn't yet is not a technicality. It's something deeper, something that lives inside the physics itself, in the very quantum loop we described a few chapters ago. Because it turns out there is a way, a legitimate, physically real, entirely within the standard model way, for that measurement to drift exactly the way it has drifted, without any new physics being involved at all. Physicists have a name for it, and, in keeping with tonight's theme, the name involves the word penguin one more time. This is, by most physicists' own admission, the single biggest theoretical headache sitting inside tonight's story. So let's take our time with it. Remember the quantum loop from a few chapters ago. The hidden side passage, the beauty quark, slips through on its way to becoming a strange quark, briefly transforming into a virtual W boson and a virtual top quark before the loop closes. That is one possible path through the loop. But it is not the only one the standard model allows. There is another path, one where, instead of a virtual top quark, the loop briefly contains a pair of virtual charm quarks. 2 of them, linked together, connecting to the outgoing pair of muons in a complicated, difficult to calculate way. This particular contribution has a name. Physicists call it a charming penguin. It sounds almost playful, but the problem it creates is genuinely serious. Unlike the top quark loop, which physicists can calculate with high precision using well-understood mathematical techniques, the charm quark loop falls into a much messier regime of quantum field theory, a region where the strong nuclear force behaves in ways that resist clean, first principles calculation. Physicists call this a non-perturbative regime, which is really just a technical way of saying the usual mathematical shortcuts stop working, and the true size of this effect is genuinely hard to pin down. And here is why that matters so much for tonight's story. Charming penguins are not new physics. They are not hiding evidence of an undiscovered particle. They are already, fully, completely inside the standard model. An old, known, entirely mundane part of the existing rulebook. But if their true size, the exact strength of their contribution to the decay, turns out to be larger than current estimates suggest, they could, on their own, produce a shift in P5' that looks almost exactly like the wobble physicists have been finding, without any new particle, without any new force, without anything beyond what the standard model already contains. In other words, it's possible, not certain, but genuinely possible, that the entire anomaly, the 4 sigma, the years of consistent deviation, the agreement between LHCb and CMS, all of it, is simply the standard model failing to account cleanly for one of its own messier internal effects. A known unknown, hiding inside a known theory, mimicking the signature of something new. Here's an analogy that might help this land. Imagine your car starts making a strange noise. It might be a genuine, new mechanical fault. Something broken that needs to be diagnosed and fixed. Or it might be a known quirk of one specific part. A part that has always made a slightly unusual sound under certain conditions that mechanics have simply never fully characterized, because it's difficult to model precisely and, until now, it never mattered enough to bother. The charming penguin is that quirk. And right now, the honest answer is, nobody fully agrees on how loud it should be. There is a real, ongoing, unresolved scientific disagreement about this. A group of theorists, in an influential paper published a few years earlier, advocated for a conservative treatment. Generous uncertainty bands around the charm loop calculation, which, if correct, would meaningfully reduce the significance of any new physics claim, because the charming penguin alone could plausibly account for much of the observed shift. But the LHCb collaborators who produced the December 2025 measurement take a different position. Their own public statements, in the months after the result was published, note that recent estimates of the charming penguin effect suggest it isn't large enough, on its own, to explain the full size of what they're seeing. In their words, a combination of theoretical modelling and experimental data suggests that the charming penguins, and by extension, the standard model itself, genuinely struggle to explain the anomaly on their own. At a workshop held at CERN in November 2025, dedicated specifically to reviewing the current state of these calculations, theorists from several different institutions presented, essentially, several different answers. Because different theoretical approaches to modelling this non-perturbative loop produce meaningfully different levels of remaining tension. So here is where that leaves us, honestly, without softening it. The charming penguin question is not resolved. The experimental physicists who ran the measurement lean toward believing this is something genuinely new. A meaningful portion of the theoretical community remains cautious, unconvinced that the standard model's own murky internal physics has been fully ruled out as the explanation. This is, in a strange way, the most honest moment in tonight's entire story. Not a triumphant discovery, not a debunking, a genuine, open, unresolved scientific disagreement playing out in real time among some of the most capable physicists alive, precisely because the answer is genuinely, currently, unknown. And it's exactly this kind of situation, a tantalizing number, sitting just below the discovery threshold, with an unresolved theoretical escape hatch still open. That has, in the history of this field, produced some of its most memorable and most humbling stories. Let's sit with those stories next. Because if you want to understand why physicists are being so careful with this 4 sigma result, you need to understand what happened the last few times a number like this appeared, and then quietly disappeared. Physicists sometimes describe the process of establishing a new discovery as climbing a ladder. Each rung represents a stage of confidence, and you are not permitted to skip any of them, no matter how exciting the view from higher up appears to be. The first rung is simple observation. You saw something. The second is statistical significance. How surprising is it, assuming nothing unusual is happening? The third is theoretical interpretation. Can existing theory, in its messiest and most generous form, explain it away? The fourth is independent confirmation. Did someone else, using different equipment, see the same thing? And the fifth, the top rung, the one that actually earns the word discovery, requires crossing that 5 sigma threshold while every rung beneath it has also been secured. Tonight's anomaly is standing on the 4th rung. Observation confirmed repeatedly since 2013. Statistical significance, 4 sigma, a real and substantial number. Theoretical interpretation, contested, as we just discussed, thanks to the unresolved charming penguin question. Independent confirmation, partial. CMS agrees, but with less statistical power than LHCb alone. And discovery, the 5th and final rung, not yet reached. Physicists know, from hard experience, exactly how important it is not to rush that final step. And the reason they know this so well is that the history of their own field is dotted with ghosts. Results that looked, for a while, exactly like tonight's story looks right now, and then quietly, undramatically, dissolved. Let's walk through the most famous one first, because it has become something close to a cautionary parable inside the physics community. In December of 2015, both ATLAS and CMS, the same 2 giant detectors that had triumphantly discovered the Higgs boson 3 years earlier, independently reported an unexplained bump in their data. Not in B meson decays this time, but in a different measurement entirely. The combined energy of pairs of photons flying out of certain collisions, clustering suspiciously around a mass of 750 times the mass of a proton. The local significance of the bump, measured within each individual detector's own analysis, was substantial, nearly 4 sigma in ATLAS. a little over 3 sigma in CMS. 2 separate detectors, again, seeing something in roughly the same place. The physics community, quite understandably, lit up. In the 8 months between the announcement and what came next, physicists around the world wrote roughly 500 separate theoretical papers, proposing new particles, new forces, new frameworks, all built to explain a bump that, for those 8 months, seemed like it might be one of the most important discoveries in a generation. Then, in August of 2016, new data came in from an additional year of collisions, and the bump was gone. Completely. No trace of it remained in the expanded dataset. It had been, in the end, nothing more than an unlucky statistical fluctuation. The kind of coincidence that, across the enormous number of measurements physicists run every year, is bound to occur somewhere, purely by chance, every so often. 500 papers about a particle that had never existed. It is not the only such ghost. In 2021, a different measurement at LHCb, testing whether electrons and muons behave with perfect universality, as the standard model insists they must, showed a deviation of roughly 3 sigma in a result that generated real excitement across the field. It was called the RK anomaly, and for a while, many physicists considered it one of the most promising cracks in the standard model's armor. Then, in December of 2022, an improved analysis, correcting a subtle bias in how electrons, specifically, were being counted in the detector, brought the measurement fully back into agreement with the standard model. A decade-long flavor anomaly, gone, resolved not by new physics but by a more careful accounting of an experimental detail. There have been others still, and each one carries its own small lesson worth sitting with. In September of 2011, an experiment called OPERA, using a beam of neutrinos fired from CERN through hundreds of kilometers of solid rock to a detector in Italy, reported a measurement suggesting the neutrinos had arrived very slightly earlier than a beam of light would have, implying, almost unthinkably, that the neutrinos had travelled faster than light itself. Had it been confirmed, it would not have been a minor correction to physics. It would have overturned Einstein's special relativity, a foundation stone underneath essentially all of modern physics, including the standard model itself. It made front-page headlines around the world within days. Physicists everywhere reacted with a careful mixture of fascination and deep, immediate suspicion, because a result this extraordinary, contradicting a century of confirmed physics, demanded an extraordinarily robust explanation. Months of painstaking re-examination followed. Eventually, the discrepancy was traced to something almost embarrassingly mundane: a fiber optic cable connecting a GPS timing system to the experiment's master clock that had not been fully plugged in, introducing a small but critical timing error of just a few dozen billionths of a second. Exactly enough to create the illusion of faster-than-light travel. Once the cable was properly seated, the anomaly vanished completely. Special relativity remained exactly as intact as it always had been. In 2003, several independent experiments reported tentative evidence for an entirely new class of particle called a pentaquark, a particle built from 5 quarks bound together, rather than the usual 2 or 3 found in every previously known particle. For a brief period, it seemed like a genuinely new addition to the particle family, a new kind of matter nobody had anticipated. As more precise, higher statistics experiments came online in the years that followed, the original signal simply failed to reappear. It faded, quietly, into the same category as the 750 GeV bump, a statistical mirage dissolved by better data. Interestingly, a genuine pentaquark was eventually confirmed in 2015 by LHCb itself, but a different pentaquark with different properties, found through a completely different, far more careful analysis than the one that had generated the original, ultimately false, 2003 excitement. And even the long-running muon G2 experiment, one of the most precise measurements ever attempted in physics, tracking a subtle wobble in how a muon's internal magnetism precesses inside a powerful magnetic field, tells a similar story of shifting ground. For years, the experimental measurement sat in persistent, tantalizing tension with the Standard Model's theoretical prediction, fueling real speculation about undiscovered particles influencing the muon's behavior. Fermilab's final, most precise measurement, announced in June of 2025, pinned the muon's behavior down to a staggering 127 parts per billion, one of the most exact measurements of any fundamental particle property ever recorded. But in the years leading up to that final result, improved theoretical calculations using a more rigorous computational technique called lattice QCD revised the Standard Model's own predicted value, narrowing the gap between theory and experiment substantially. The anomaly did not vanish entirely, the way the 750 GeV bump or the RK result did, but it shrank and shifted from what once looked like a clear experimental discrepancy into something now understood to depend heavily on which theoretical calculation you trust most. A reminder that sometimes the ghost isn't in the experiment at all. Sometimes it's hiding in the prediction. None of this means tonight's anomaly is destined for the same fate. The physics is genuinely different in important ways. This is not a single bump in an energy spectrum, prone to random statistical noise the way the 750 GeV excess was. It is a specific, well-motivated angular observable, built by theorists over years specifically to be sensitive to exactly this kind of new physics, and it has now persisted consistently across 4 separate LHCb analyses spanning more than a decade, plus an independent confirmation from CMS. But this history is precisely why physicists reach for caution rather than celebration at 4 sigma. Not because they are pessimists, because they have learned the hard way more than once what it costs. In wasted years, in 500 discarded papers, in public credibility, to celebrate too early. So the honest, unresolved question sitting at the center of tonight's story is this. Is the 4 sigma deviation in this rare, quiet penguin decay of a B meson the long-awaited first genuine sign that the Standard Model is finally, truly incomplete? Or is it the next entry on this list, quietly making its way toward disappearing as more data arrives? Nobody currently alive knows the answer. Not the physicists who ran the analysis. Not the theorists debating the size of the charming penguin effect. Nobody. And there is something worth sitting with in that uncertainty rather than rushing past it. We'll come back to that feeling later tonight. For now, let's follow a different thread outward, because even if this specific anomaly turns out to be a ghost, the reason physicists are hunting this hard in the first place connects to a mystery far larger than any single particle decay. A mystery that touches on the very reason anything, including you listening to this right now, exists at all. Here is a question that sounds almost too simple to be one of the deepest unsolved problems in physics. Why does anything exist at all? Not, why does the universe exist in some grand philosophical sense? We'll leave that question for the physicists to argue about over coffee. A narrower, sharper, more answerable sounding version. Why is the universe full of matter when the basic laws of physics say it shouldn't be? Here's the problem, laid out plainly. According to the simplest and most natural reading of the Big Bang, the enormous burst of energy that created our universe should have produced matter and antimatter in exactly, perfectly equal quantities. Antimatter is not a science fiction invention. It's real. It's been created and studied in laboratories for decades, and it consists of particles identical to ordinary matter in every way except one. Their electric charge and a few related quantum properties are flipped. An electron's antimatter twin, called a positron, has the exact same mass, but a positive charge instead of a negative one. And when a particle of matter meets its antimatter twin, something dramatic happens. They annihilate each other completely, converting their entire mass into a burst of pure energy, leaving nothing behind. So, if the early universe produced matter and antimatter in perfectly equal amounts, as the simplest physics suggests it should have, then as the universe cooled and expanded, every single particle of matter should have eventually found its antimatter twin and annihilated. All of it. Completely. Leaving behind nothing but a uniform, cooling bath of radiation. No galaxies. No stars. No planets. No chemistry. No you. And yet, here we are. The observable universe, when astronomers look at it, is overwhelmingly, one-sidedly dominated by ordinary matter. Antimatter, out in the cosmos, is remarkably rare. A curiosity, not a co-equal partner. Something, somewhere, in the earliest moments after the Big Bang, tipped the scales. Ever so slightly. Physicists have actually measured how slightly using detailed observations of the faint afterglow of the Big Bang itself, the cosmic microwave background. The number they arrive at is almost impossibly small. For roughly every billion pairs of matter and antimatter particles that existed in the infant universe and subsequently annihilated each other, there was, on average, one single extra particle of matter left over, with no antimatter partner to annihilate against. 1 in a billion. That tiny, almost invisible imbalance. One extra particle of matter, surviving for every billion pairs that destroyed each other, is the leftover residue that eventually became every galaxy, every star, every planet, every atom in your body, and every atom in the body of everyone you have ever loved. We are, quite literally, made of a rounding error, a statistical leftover. The universe's version of a coin that landed, ever so slightly, more often on one side than the other, across an almost inconceivable number of flips. So the real question becomes, what caused that tiny imbalance? What broke the perfect symmetry between matter and antimatter in the earliest fraction of a second after the universe began? Physicists have a partial answer, and it involves something called CP violation, a small, measurable asymmetry in the way certain particles behave, first discovered in 1964 in the decays of particles called kaons, a discovery that won its own Nobel Prize. CP stands for charge conjugation and parity. Essentially, applying CP to a physical process means asking, if you swapped every particle for its antimatter twin and reflected the entire process in a mirror, would the laws of physics look exactly the same? For years leading up to 1964, most physicists assumed the answer was simply yes, always, without exception. That this particular symmetry was as fundamental and unbreakable as the conservation of energy itself. Two American physicists, James Cronin and Val Fitch, running a careful experiment at Brookhaven National Laboratory, decided to test that assumption directly, studying the decays of a particular type of kaon. What they found startled the field. In a small but unmistakable fraction of decays, roughly 2 in 1,000, the kaon violated the expected symmetry. Matter and antimatter, reflected through this specific interaction, did not behave quite the same after all. It was a small crack, but it was the first one anyone had ever found, and it forced physicists to accept that the universe's rulebook contained, somewhere within it, a genuine asymmetry between matter and its antimatter mirror image. Cronin and Fitch shared the Nobel Prize in Physics for the discovery in 1980. 3 years before that discovery was even made, in 1967, a Soviet physicist named Andrei Sakharov worked out, from first principles, exactly what conditions the universe would need to satisfy in order to end up matter-dominated rather than perfectly symmetric. He identified 3 requirements, now known as the Sakharov conditions. There must be interactions capable of changing the total number of matter particles relative to antimatter particles. The universe must, at some point, have departed from thermal equilibrium, and, critically, directly relevant to tonight's story, There must be a genuine violation of CP symmetry, exactly the kind of crack in the mirror Cronin and Fitch would go on to discover. Sakharov proposed this framework years before there was any experimental evidence that such a violation even existed. When Cronin and Fitch found their kaon result shortly afterward, it slotted directly into the third of his 3 predicted requirements. Another quiet, unglamorous example of theory anticipating experiment in a field that has made a habit of it. For most of physics, the answer is yes, but not entirely. In certain weak force interactions, including, as it happens, in the very same B meson decays LHCb specializes in studying, the laws of physics behave very slightly differently for matter than for antimatter. It's a small effect, but it's real, measurable, and repeatable. Here's an image that might help. Imagine a mirror that is almost, but not quite, perfect. Almost everything reflected in it looks exactly correct, but there is a tiny hairline crack running through the glass, and anything reflected precisely along that crack comes back very slightly, almost imperceptibly, distorted. That crack is CP violation. And it is, physicists believe, the reason a small sliver of matter survived annihilation in the earliest moments of the universe, while its antimatter twin did not. There's just one problem. When physicists calculate exactly how much CP violation the standard model actually predicts, using the equations we described earlier in tonight's journey, the number comes out far, far too small. Somewhere between 100 million and 10 billion times too small. In fact, to account for the matter-dominated universe we actually observe. The crack the standard model predicts in the mirror is real. It has been measured. It exists. But it is nowhere near large enough to explain why anything survived the annihilation at all. Which means, almost certainly, there is more CP violation somewhere in nature than the standard model currently accounts for. A bigger crack, hiding somewhere in the mirror, that physicists simply haven't found yet. And this, finally, is why the quiet wobble in a rare B meson decay, buried in a mountain of 500 billion data points, connects to something as vast as the existence of matter itself. Because that hidden quantum loop we described earlier, the penguin loop, where a beauty quark briefly slips through a virtual side passage on its way to becoming a strange quark, is exactly the kind of place where new sources of CP violation could be hiding. If an undiscovered particle is entering that loop, it could be carrying an entirely new complex phase, an entirely new crack in the mirror, contributing to exactly the kind of asymmetry needed to explain why the universe is not empty. To be completely clear about where the evidence actually stands tonight, no direct link has been established between this specific penguin anomaly and the matter-antimatter puzzle. It remains, honestly, a hypothesis. A tantalizing connection some physicists find plausible, not a measurement anyone has confirmed. But it is precisely why a decay this obscure, this rare, this seemingly small, occupies so much of the attention of physicists working on the deepest open questions in the field. And in March of 2025, LHCb made real, confirmed progress on a closely related front, reporting, for the very first time, the observation of CP violation in a different kind of particle entirely, a baryon called the lambda B, made of 3 quarks rather than 2. It was the first time this particular kind of matter-antimatter asymmetry had ever been directly observed in this class of particle, extending 60 years of CP violation research into an entirely new sector of the particle world, and adding one more small, hard-won piece to a puzzle physicists have been assembling since 1964. The mirror, in other words, is being mapped, crack by crack, decade by decade. And tonight's anomaly might be a glimpse of one more crack, somewhere physicists haven't fully charted yet. But to study a crack in the mirror properly, physicists eventually needed to build something extraordinary, a place to hold antimatter itself, safely, long enough to study it directly. And that facility exists. It's real. It's underground, not far from where LHCb sits. And what happens inside it is, genuinely, one of the strangest and most delicate feats of engineering on Earth. Somewhere within the CERN complex, separate from the Large Hadron Collider entirely, sits a facility with a name that sounds almost like something out of fiction. It is called, officially, the Antiproton Decelerator. But physicists there refer to the broader complex, more evocatively, as the Antimatter Factory. Here is what happens inside it, and it is worth picturing slowly, because it is genuinely strange. High-energy protons, accelerated separately from the main collider ring, are smashed into a solid metal target. In the violence of that collision, some of the energy released converts, briefly, into new particle pairs. Among them, pairs of protons and antiprotons created directly out of pure energy, exactly as Einstein's equations allow. The antiprotons are magnetically separated out from the debris and funneled into a machine called the Antiproton Decelerator, which does something almost paradoxical for a particle accelerator facility. It slows them down, dramatically. From nearly the speed of light down to just a few % of it, using a sequence of electric field braking and a delicate technique called stochastic cooling, which gently nudges the antiprotons into a tighter, calmer, lower energy beam. Then comes the truly delicate part. A collaboration called LHCb takes these cooled antiprotons and combines them with positrons, the antimatter twin of the electron, produced from a radioactive source and gently captured in an electromagnetic trap. When an antiproton and a positron find each other under the right conditions, they can bind together into a complete atom of antihydrogen. A positron orbiting an antiproton, the perfect antimatter mirror image of the simplest atom in the universe. And now, here is the genuinely hard problem. How do you hold on to an atom of antimatter? You cannot put it in a container, because the moment it touches any ordinary matter, the walls of a jar, a table, the air itself, it annihilates instantly, converting itself into a small burst of gamma radiation and vanishing completely. Antihydrogen has to be held without ever touching anything solid at all. The solution physicists engineered is called a magnetic bottle, technically an Ioffe-Pritchard trap. Because a neutral antihydrogen atom carries a tiny magnetic dipole moment, physicists can construct an arrangement of magnetic fields with a very specific shape, strong at the edges, weakest exactly at the center, that gently pushes any low-energy antihydrogen atom back toward that central minimum, no matter which direction it drifts. The atom is, in effect, floating in a bowl made not of matter, but of pure magnetic field, suspended in a vacuum, touching nothing for as long as the trap holds. Any antihydrogen atom that strays too far or moves too energetically escapes the bottle's grip and touches the chamber walls, and annihilates instantly in a tiny, precisely recorded flash. Physicists literally watch these individual annihilation events, one atom at a time, to confirm what they've caught. For years, this process was agonizingly slow. Producing even a modest sample of trapped antihydrogen atoms could take weeks of careful, patient work. Then, in November of 2025, the ALPHA collaboration reported a genuine breakthrough, published in the journal Nature Communications. Using a new technique, sympathetically cooling the antiprotons with laser-cooled beryllium ions before combining them into antihydrogen, the team increased their production rate roughly eightfold. Over 15,000 antihydrogen atoms trapped and studied in under 7 hours. The same task that had previously required about 10 weeks of continuous effort. The spokesperson for the ALPHA collaboration, physicist Jeffrey Hangst, described the moment plainly. These numbers, he said, would have been considered science fiction just 10 years earlier. Why does any of this matter for tonight's story? Because once you can hold antihydrogen steady, you can study it directly, measuring its light spectrum, its energy levels, the precise transitions its lone positron makes as it moves between orbits, and comparing every single one of those measurements against ordinary hydrogen, the best studied atom in all of physics. If antihydrogen behaves in even the slightest way differently from ordinary hydrogen, if there is any measurable asymmetry at all between matter and its antimatter mirror image beyond what's already accounted for, it would represent an entirely new source of CP violation, an entirely new crack in the mirror, a direct physical measurement of exactly the kind of asymmetry the universe needed in its earliest moments to leave any matter behind at all. So far, remarkably, every measurement of antihydrogen has matched ordinary hydrogen with extraordinary precision. The mirror, at least in this particular test, remains unbroken. But the tools to look more closely, more precisely, at faster rates than ever before have only just become available. And physicists working in that underground facility, right now, tonight, while you listen to this, are continuing to look. There's even a related experiment called ALPHAG that has begun testing something that sounds almost too strange to be real. Whether antimatter responds to gravity the same way ordinary matter does. Its first result, reported in 2023, found that yes, antimatter, when released, falls downward, just like everything else. A small, quiet confirmation of a very deep assumption in physics, verified directly, for the first time, on an actual sample of trapped antimatter. So now we have two separate threads of tonight's story running in parallel. A quiet wobble in a rare particle decay discovered 100 meters underground in one detector, and a delicately trapped sample of antimatter held in a magnetic bottle a short distance away in a separate facility, being tested for the exact same kind of asymmetry. Neither thread, on its own, has produced a confirmed discovery yet, but both are aimed, in different ways, at the exact same underlying question. The same crack in the mirror, the same missing piece of the story of why anything exists at all. Which brings us, finally, to the part of tonight's story where physicists allow themselves to speculate, carefully, conditionally, but out loud, about what might actually be causing all of this if the anomaly turns out to be real. Here is an important boundary to draw clearly before we go any further into this chapter. Everything you are about to hear is speculative. None of it has been confirmed. All of it depends entirely on an assumption we have not yet verified, that the anomaly survives the coming years of additional data and eventually crosses the 5 sigma threshold with the charming penguin question fully resolved. If either of those things fails to happen, nothing in this chapter describes reality. It describes possibility. With that boundary firmly in place, here is what physicists are quietly considering in the back of their minds as candidate explanations if this turns out to be real. The leading candidate is a hypothetical particle called a leptoquark. Every particle in the standard model belongs to one of two families: quarks, which build protons and neutrons, and, ultimately, atomic nuclei, or leptons, which include the electron, the muon, and the neutrinos. In the entire history of particle physics, no particle has ever been found that bridges those two families directly, coupling to a quark and a lepton at the exact same interaction point. A leptoquark would do exactly that. And if one exists, with roughly the right mass and the right coupling strength, it could insert itself directly into the quantum loop we described earlier, sitting alongside the ordinary standard model contributions, and shift the angular measurement, p5', in precisely the observed direction. It would fit the data almost too neatly. Direct searches for leptoquarks, using ATLAS and CMS to hunt for them being produced outright in high-energy collisions, have so far found nothing, which has allowed physicists to rule out leptoquarks below roughly 1 to 2 trillion electron volts in mass. But that still leaves an enormous amount of unexplored territory above that threshold. Territory current colliders may or may not be powerful enough to reach directly. A second candidate is something physicists call a Z-prime boson. Essentially, a heavier, undiscovered cousin of the familiar Z boson that carries the weak force in the standard model, but one that couples differently to different generations of particles. If a Z-prime existed that talked to muons differently than it talked to electrons, it could produce exactly the kind of pattern seen in this anomaly, provided its mass sits high enough, likely several trillion electron volts. to have evaded every direct search conducted so far. A third possibility involves an extended version of the Higgs sector itself. Theories where, instead of the single Higgs boson discovered in 2012, there exists an entire family of Higgs-like particles, including electrically charged versions that could also slip into the quantum loop and contribute to the shift. There are more exotic possibilities still. Extensions involving entirely new categories of force and grand unified theories that attempt to merge all of known physics into a single overarching framework, some of which naturally predict leptoquarks as a required consequence of their deeper structure rather than an awkward add-on. And then there is supersymmetry. For decades, one of the most popular and most extensively studied theoretical frameworks in all of particle physics, proposing that every known particle has a heavier, undiscovered superpartner. Supersymmetric particles, in principle, could also shift this measurement. But after 15 years of dedicated, expensive, painstaking searches, the Large Hadron Collider has found no direct evidence of supersymmetry at all, ruling out enormous swaths of the theory's most natural parameter space and leaving the masses required to explain this specific anomaly sitting uncomfortably close to regions already excluded by direct experiments. It is worth being honest about what even a confirmed discovery here would not immediately mean. It would not automatically solve dark matter. Some theoretical models do connect flavor physics and dark matter together, but none of them are required by this measurement alone. It would not mean gravity has been unified with the other forces. Quantum gravity remains an entirely separate, unresolved problem, and it would not, on its own, explain why neutrinos have mass. That puzzle sits in a different corner of physics altogether. What a confirmed discovery would mean, at minimum, is this: the discovery of an entirely new fundamental interaction, or an entirely new particle that has never appeared in any experiment in the history of physics. The biggest single addition to the 17-particle inventory since the Higgs boson was confirmed in 2012, and arguably the most significant departure from the Standard Model's core structure since the model was first assembled 5 decades ago. That is what is actually at stake, sitting quietly on the 4th rung of a 5-rung ladder inside a mountain of 500 billion decay events underneath the French-Swiss countryside. So, where does that leave things right now, tonight, as you're listening to this? Let's take stock of exactly where the story stands and what happens next. Before we take stock of exactly where tonight's story stands, it's worth slowing down for the timeline itself. Because this is not a discovery that arrived in a single afternoon. It is the product of well over a decade of patient, incremental work and understanding that arc makes the honesty of the current moment easier to sit with. The very first hint of tonight's anomaly appeared quietly back in 2013, when LHCb, using an early batch of Run 1 data, noticed a local deviation in the P5' measurement of a little under 4 sigma. It was interesting. It was not yet something anyone was prepared to build a public claim around. In 2015, a fuller angular analysis using the complete Run 1 dataset confirmed the same pattern. In 2020, an expanded analysis, folding in additional data collected in 2016, found that the deviation had not gone away, had not weakened, had not resolved itself the way so many early anomalies quietly do. It persisted. Then, in November of 2024, the CMS collaboration entered the story directly, submitting their own independent angular analysis. The second witness we discussed earlier, built from 140 inverse femtobarns of Run 2 data, and presented publicly the following year at a major physics conference in Boston. In September of 2025, CERN released an official public summary of LHCb's definitive Run 1 plus Run 2 legacy angular analysis. The culmination of over a decade of accumulated data, presented by physicists Mark Smith and Leon Karus, confirming that the tension with the Standard Model remained, and noting explicitly that the results agreed well with the independent CMS measurement. Barely 6 weeks later, in early November of 2025, a dedicated workshop convened at CERN itself. The 15th in an ongoing series focused specifically on the theoretical implications of LHCb's measurements, bringing together theorists from institutions across the world to argue, in real time, over exactly how large the charming penguin contribution genuinely is, and exactly how much of the observed anomaly it might explain away. Then, in December of 2025, the full formal paper was submitted. The 650 billion decay analysis, the 4 sigma tension,